right, so everybody, now it's a part of the episode where I'm going to introduce you all to a model called K nearest neighbors. And let's talk about how K nearest neighbors works. So K nearest neighbors is a classification model similar to decision trees, similar to random forest, but instead of the inner workings are different. The inner workings are based on what the nearest neighbors to a data point are. So let's talk about how this works. KNN is a supervised algorithm, just like all of our classification tasks. It's a supervised machine learning task, except instead of playing 20 questions with the data, yes or no questions, like we did with trees, we're making predictions based on how close new data points are to known classified labeled data points. So this is a distance-based algorithm. Some details, this is considered a lazy algorithm. Now lazy has a special meaning in computer science and in computation. What that means is that it will not construct a general internal model, but evaluates the data when it needs it. That's what lazy means. It evaluates when it needs the data, not before. Our classification is computed from a simple majority vote, a simple majority rule of the K nearest neighbors of each point. What the heck is K? K is a variable. K does not come from the model itself. So we have to supply K. So if the question is, Ryan, what's the right K to run? It depends on your data. 100% depends on the data itself and the distances between the data points, okay? And we'll talk about how to handle that and come at a best guess for deciding on a K. Because if we have K of 1, that's one model. If we have a K of 5, that's a second model. If we have a K of 10, that's a third model. So each model is different. What goes on underneath the hood, our predictions are made on new data points by searching through the entire training set for the K most similar instances. That's what the K means is, look, if K is 2, look at your 2 nearest neighbors. K is 7, look at your 7 closest neighbors for each data point and classify based on the majority rule. Yes, Greg.
Because, let me call your question on how this may relate possibly working to a precision tree. So is it on the K nearest neighbors is looking at a certain variable at a time? Like, so for example, if we look at like age, you know, we've got a Titanic data set that has age, gender, or whatever in it. Is K nearest neighbors running one K nearest neighbor and looking for distance for all those variables?
For every data point.
Yes. How does it calculate that if you've got a precision and for some kind of plane, for example, how does it know where to put it when there's many different possible variables?
Yeah, we're plotting. I mean, it's having measurements in higher dimensional space. It's just Euclidean distance or Manhattan distance, depending on. Look, let me give you all a visual. So here's our algorithm here. If we've got yellow, green, and orange data points, notice the yellow, orange, and green, let's call those our labels. We know the color of those data points. Now this gray data point that's new, we have not yet classified that. And that's the whole game of supervised machine learning. You have answers for your training set, but you don't have answers for new stuff. So the gamble, the hope is that your out of sample data set is very similar to your in sample data set, right? So let's take a look at this. We calculate the distances from each of our new data points to the existing labeled data points. It's all just distance measuring, right? And we could use different distance metrics. Let's keep it real simple, just use Euclidean distance. If the thought of what in the heck is Euclidean distance is challenging, I'll give you an analogy. As the crow flies is Euclidean distance. And even if you're in 10-dimensional space, as the crow flies is the shortest distance between points. Okay. So we're calculating all of the distances between all of the points, but let's talk about the K part. So of these data points, I have 2.1 millimeters or whatever the distance is, 2.4, 3.1, 4.5. So if we go with a K of 1, we classify that data point based on what its nearest neighbor is. That's it, K of 1. The first data point that was closest was 2.1 away. It's yellow, so we classify yellow. If we set K to 2, we go with the consensus of the two closest data points. Well, they're both yellow, ergo the prediction is yellow. If we set our K to 3, then we also include this green point that's farther away, and then we take a consensus of those top 3, it's yellow. If the K is 4, again, we take the consensus and yellow wins out, just because of the relationship of the data in this example. So your K changes, your K is part of the model, but the model does not define the K. You define the K, and kind of like max depth, we'll run this in a for loop to decide the best K, right? And the best K is going to be different for different data sets. There's not a magic number. It's not 2, it's not 7, it's different based on the data sets. So let's camp out on this, visual for just a moment. And I want to open up to questions, clarifications, comments, anything that you'll need to make sure that you have an understanding of how K nearest neighbors works. Great.
I think the issue of having is I'm trying to, like, since Euclidean distance, and I'm in the brain trying to picture distance in number of dimensions.
Just don't.
So I guess yeah, I mean, I guess this is literally just operating in four dimensions.
Then we can conceive of with our people brains. Yeah, or at least visually.
So I guess an overly simplified way to describe this, it's just comparison. It's comparing all of the points, all the variables between two things, and then finding some way to assign that difference.
Yeah.
Score about
Yeah.
distance.
Yeah. So like Euclidean distance in a two-dimensional space is a hypotenuse between the difference in X and the difference in Y. And if we were in 3 space, the Euclidean distance between 2 points would be the hypotenuse. Yes.
Possible.
As the crow flies. Yeah. Folks at home, any clarifying questions, comments on how, anything that we can visit about how K nearest neighbors is working right now? Pretty similar.
Yeah, I have a question.
But I want to open up for y'all. Was that Kyle? Go ahead.
Yes, sir. So I was wondering if, let's say K equals 3 and we have the 2 yellows and the 1 green, right?
Yeah.
Does it assign like a weighted distribution of likelihood for like each classification, I guess? So like, does it just say, oh, it's just yellow, or does it say like, okay, okay, got it.
Yep, uniform by default, or we could change that to distance so that we're weighting points inverse to their distance.
Okay.
Is another option, but yeah, uniform is perfectly fine, default.
Okay.
Yeah.
Cool. Thank you.
I saw Arsene. Did you have a question, Arsene?
It was the same question.
Oh, okay, cool. Vasily?
I think I may have gotten a little lost on this diagram where the votes come in.
Yeah, let's talk about that. So we have all of our data points that are labeled yellow, green, and red, right? Or orange. Each new data point, we don't know what its label is. So this whole model is predicated on the idea of similar things will have similar distances, right? Similar things will be similar, and dissimilar things are dissimilar, right? So your model will calculate distances between its neighbors, and the K part, is how many neighbors are we going to ask this data point to pay attention to? That's where the K is going to come in. So if we say, if your K is 1, we're saying classify yourself as your closest neighbor. If the K is 1. If the K is 2, then we say classify yourself as your as the consensus of the two closest neighbors.
So these isn't necessarily like a different variable. It could be safe, right?
The neighbors are labeled, are data points from your train,
Right. Okay.
and that's why they're labeled. So if we throw in 100 new data points that are unlabeled, they don't pay attention to each other. They pay attention to the labeled data and the distances there. And it's all based on consensus. And if there's a tie between the first two, it'll go with the closest based on the uniform. Yeah, pretty straightforward. It's all about what's close by. So we have a bunch of pros. K nearest neighbors, it's very simple to implement. So even if sklearn didn't exist, you could program K nearest neighbors with a Euclidean distance formula. It'd be real dang easy. And then a majority vote formula. Very robust to noise in the training data set, which is great. It's effective if our training data set is very large. And our calculations are performed just in time. I mean, that's part of the laziness, the just in time. Means that when the prediction is needed, we perform the calculation rather than opposed to ahead of time. So that's kind of cool. Now, this is very, very cool. Our training instances can be updated and curated over time to keep our predictions accurate. So we can retrain this. There are some cons. You need to determine the value of K. Our computational cost is also really high compared to a decision tree or a single tree, because we are computing distances between each data point and the training samples that are close by. I see a question from Kate and then Fred. Go ahead.
Yeah, I just wanted to confirm that when we're talking distance here, it's a function of all of the dimensions.
Yep, all of the dimensions that the model is trained on. Yep.
And then is that distance then relative to the units of the dimensions? Because I'm thinking like Titanic, there's a lot of 0 1s. Okay, so it weights them equally in that sense?
The weighting of the distances is a larger question that we'll talk about with scaling. So if you don't mind, I'll talk about the weights of distances with scaling. Because it can be confusing to think of if we have dollars in one column and millions of miles in another column, dollars and millions of miles, the ranges are very different. So we want to pay attention to like the relative space, the relative distances, but we got to walk before we run. Will that work for now, Kate? Cool. Fred?
I wanted to ask, so that last point that you is that refer only to the data being measured in relation to labels, or does it also kind of broadly change the fact that labels themselves change to make a change in our definition, like if you look at
It's not dynamic on its own, no. But we could retrain it. Once we've classified some new data points, we could retrain it over time.
yeah,
Like we could with a lot of models, actually.
we're just starting to say, track change, like text on Titanic, like dynamic over time, they'll change the survival odds on the bottom.
Yeah, I see Arsene and Kyle. I don't recall who had their hand up first.
I'll just go. There's gonna be a lot of binning then of the data.
There's going to be a what now?
Some binning of the data.
No, not necessarily. There's no
Okay.
need to bin.
Okay, because relative to Kate's question, you said that sometimes categories are difficult. It's difficult to relate categories because of their their volume.
Yeah. If you're comparing millimeters to millions of dollars, those are different scales. I promise everyone, we're going to talk about scaling in the next module in regression. And that means, so I'm going to tell you right now, scaling will improve the performance of a K-nearest neighbors model because it's based on distance, but y'all are still wrangling with encoding. right? I don't want to throw in coding and scaling at y'all right now. Does that speak to your question a little bit, Arsen?
Thank you.
I promise y'all, we'll talk about scaling. It's just too much too fast if we do encoding and scaling.
Oh, no problem.
We've
It
tried
just seemed
before.
like,
Yeah,
yeah, it just seemed like it was gonna come to that, here. But yeah, if we're gonna talk about it later, totally fine.
yeah. So you're going to build your first K nearest neighbors model right here. And I'm willing to bet y'all that we'll have some more interpretable models when we scale, but for now, we just got to walk before we run. Go ahead, Kyle. What's on your mind?
So I'm sorry if this is getting too deep into the weeds here, but let's say K equals 4
Okay,
and the closest one is yellow and the next two are green and then the last one's yellow, right? And let's say yellow is like really, really close for the first one and the second one is really far away and the two green ones are basically in the middle.
sure.
Is there a metric that we would be able to look at to see stuff like that, or does it just kind of make a decision, or
Yeah.
is
off the
that
top of
coming
my
into
head-
the weighting?
Yeah, off the top of my head, Kyle, I'm not sure, but if you used, the default weighting is uniform.
Right.
You use distance, you would weight the points inversely to their distance. So let's see, closer neighbors of a query point have a greater influence. So we can change that hyperparameter and say
Right.
your nearest neighbor, the nearest of the nearest neighbors have more influence.
Okay.
But yeah, if there's a tie, my guess off the top of my head is it's going to go with the closest tie.
Okay.
But we're also talking about, 5 variables at a time and 5 states.
Right.
Yeah,
right.
so I'm not gonna
Okay.
worry too much about that. But yeah, the big two right here is uniform is the default weighting, and distance, you could change that, and you can even build your own custom function, which is
Right.
kind of crazy.
Nice.
The defaults here are at the risk of getting too mathy. The metric is Minkowski distance. That's Euclidean distance and Manhattan distance. And Manhattan distance is taxi cab. It's city block distance. So when I say Euclidean distance is as the crow flies, Minkowski is Euclidean and Manhattan, but the P of 2 is setting the dimension of that to 2, which is Euclidean. And we are not going to go into non-Euclidean geometry in this class. Yeah, that's for your
appreciate it.
weekend. Y'all gotta have something to do on the weekend. Cool. Let's see some code. Let's see. Oh, another con. I forgot to mention this last con. Distance starts breaking down in very high dimensions as a measurement. So this is the curse of dimensionality. 2 things are happening with the curse of dimensionality. Computation increases exponentially with each column, exponentially. The exponent is literally the number of columns, right? Another thing that happens with the curse of dimensionality, we might think, yeah, more data is better, but more columns means that distance starts breaking down. Let's talk about distance, right? A hypotenuse on a 2-legged triangle is easier to understand than a hypotenuse on a 58-legged triangle. And each new leg provides less and less information at higher and higher computational costs. Kind of wild, huh? So if you have, so here's your punchline. If you have like, I don't know, 400 features, I would not do K nearest neighbors first. Maybe those 400 features all need to be there. Maybe 100 of them need to be there. I don't know. But K nearest neighbors would take a long time to train, and because it's a distance-based metric, even if we scale things, the more columns we have, the less distance is that valuable. So that's something to keep in mind. I'm going to check the chat here.
Well, I have a quick question.
Oh yeah, go ahead, Jules.
With that in mind, is that where really like feature engineering comes into place, like where distance does matter,
Yes.
but you need
Yeah.
to lower the number of features in order to get it to work.
In order, yeah, lowering features will not just make it work, it'll make it work better.
Okay.
Yes, feature engineering is your friend when you have a scenario like 400 features, absolutely. That will have benefits not just to distance-based metrics, but other models like trees as well. Yeah. Yes, cursive dimensionality is a thing. So less features is better. Would this be a bad test when the possible outcome is target variable? Very likely it would scale. Yes, absolutely, Kate. And right now we are not scaling our data points, but we will. We will soon. And Greg, did you have a question? I thought I saw.
I did, I think, I may have come answer, but I was gonna ask the difference between. When I think of clustering, I think of distance, but it's like clustering is categorical as opposed to numerical. In terms of its input. So the reason I was asking was when I'm looking at something like neighbors distance, I think of clusters of things that are like each other.
Okay.
So I'm kind of worried that's clustering, but.
It's not directly, so k-nearest neighbors is classification, not clustering. Clustering is an unsupervised algorithm where it groups like points based on, well, k-means. Now, here's one for y'all. Here's a little confusion. Write this down. It'll totally be on an interview question somewhere. What's the difference between k-nearest neighbors and k-means? They both have k in them. K-nearest neighbors is what we're learning right now. K-means is a clustering algorithm we'll learn in clustering. Now they both use k, that's determined by the human being. They both use distance, but one is a classification task, the other is a clustering task. And they're cousins, Greg, is my best example, but I don't want to introduce clustering just yet. It would be premature. But we look at this data and we kind of see 3 clusters, but we also have the answers. So we'll talk about clustering a little bit later. Cool, let's get into some code. Do our imports. I'm going to pull in Iris and do a little bit of prep. And here's something to note. The Iris data set, the sepal length, the petal width, petal length, all of those variables, we would not need to scale these because they're on the same, they're on millimeters or centimeters anyway. So relative to each other, they have the same measurements. But if you're comparing millimeters to millions of dollars, that's where scaling comes in as more valuable. And we'll talk about scaling when we talk about scaling. For here, like telco, it isn't going to be a big scaling deal either because we have dollars. We have dollars and number of tenure months. So we only have 2 measurements. So it's not that big a deal. Yeah, cool. And we're going to train test split. And we're stratifying based on the target variable of species. And then we'll separate our X and Y variables, and train our model on our model on train. So the first thing that we do is make the model, an empty model. We're setting our arguments, our hyperparameters, the weighting. This is actually a duplication. The default weight is uniform. The default K is 5. They just picked a number out of the hat for the default. It's generally pretty good, but we can play with it. We can play with that and tune it. So make the object, fit the model, and then use the model to make predictions. And we could either call .proba to get the probability, or .predict to get the prediction. That's where the right pred is getting the prediction. Or we could also get the probabilities of the prediction. That's pretty cool. No attribute head. Oh, it's because it's a NumPy array. So we'll say just give me the first 4. And so it's pretty darn sure about these ones and about this last one. or the second to the last of the first four, it's 80% sure about one species versus the other. So K nearest neighbors is pretty cool because we can classify multiple outputs, not just binary, multi-class outputs. So we could, if we had, this would work with iris with 3 species. This could work with something where you have 5 categories or 10 categories. So let's evaluate on our in sample. Ooh, 99% accurate on in sample. That's cool. And let's run a classification report. Accuracy is great. Recall is pretty good. If versicolor is the positive case, all right? Not too bad. Okay. Let's see. Okay, perfect. So if we wanted to manually work through this, we could manually work through a labeled data set. So this is what I'm sharing here is we have 4 different measurements, A, B, C, D. So we have 4-dimensional geometry. Don't freak out. Just let the model worry about it, right? Everything's cool. And then our target variable is versicolor, Setosa, virginica accordingly. Okay. And if we were to add new unlabeled observations, that's what this new obs is doing. So new obs is kind of like validate, right? And based on the similarity in distances, and we can classify similar things, right? I want to go on a little aside super quick. It may feel counterintuitive that we're talking about higher dimensional space, right? But let's say we have an X variable, a Y variable, let's see, an A, a B, and a C. Let's say we have 6-dimensional space, right? If your first row is 1, 1, 1, 1, 0, 1, and your second row is 1, 1, 1.9, 0, 1, those are pretty darn close, aren't they? What if we do 0.8, 0.9? 1, 1, 0, 1. That's still pretty close. What about something else that's 0, 0, 0, 0? 5, 0. That's farther away, isn't it? Congratulations, everybody. You're doing higher dimensional distance math in your head. Are y'all with me? Cool. And even if these were binaries, right? Binaries can have distance. Yep. Hit the wrong button. So it's, and what if we had something that was like off by this? Well, this last row is just a little bit closer to the first 3, right? Now, the measurement of how many or how much per column, we don't have to do the arithmetic in our head, but you can already see what's close and what's not close, right? Cool, congratulations. Higher dimensional math, doing distance calculations in your head. And even with when we are using higher dimensions in space, the Euclidean variables end up just being the same, right? So if we had 2 dimensions, our hypotenuse, c squared, would be equal to a squared plus b squared, right? Well, what if we have super duper crazy higher dimensional math? Well, c squared, or like a squared here, could be x squared plus y squared plus z squared plus whatever. It's just the hypotenuse calculation with more legs. Yeah, Mindy.
If you have your dummy variables though, and you drop the.
You drop first.
Yeah, thank you. This. Like.
No, because when you drop first, so Mindy's question was, was a good one. If we drop first, is this going to influence things? And the answer is no, because when you do get dummies, let's say we have red, green, blue as our possibilities in a column, we then get an is red column, an is green column, and an is blue column, right? And this could be one hot encoding means that only one of these is available at the same time, right? So we can't have multiple ones on the same line because something can't both be red and blue. That'd be upside down, right? If we drop first, we drop red. So we drop that column. But so this begs the question, what color is row 6? It's blue. What color is row 6? Row 5, it's blue. What color is row 4? It ain't blue, it ain't green, it's red.
So when you do your neighbor, you're looking for red. And so you have to be like, oh, it's not. Like, would it show? I guess, okay, because
It's all good.
doesn't matter, like,
Doesn't matter.
it just happens. Got it.
Yeah, if you dropped more than the first, you would have a problem because then you're destroying data.
Okay.
But because of process of elimination, you always have it. If you want to be extra feel extra secure, extra safe, you can not drop the first. It's not going to have any influence.
I feel like it's kind of like the same thing that is like the math of it. You know, if you let that extra column in, it's still going to be a difference of 1.
Yeah.
Right, so regardless of where that difference is, it's still difference 1 to the math is not the same.
Bingo. And even, I mean, especially, it's easier to figure that out on a binary. Since if one column's turned on, the other column's turned off, or one column's true, one column's false, there's zero entropy between them. There's no information gain or information loss since they're perfect inverses. Cool. So as always, oh, go ahead. I see your hand, Arsene. Go ahead.
Yeah. Oh, I was gonna ask about the calculation that you tried to make. Does that mean that all the values for all the, I would say, hypothetical sides of triangles are put into the a square value that you? Okay.
Yeah. Yeah. The Euclidean distance formula, all it is Pythagorean theorem. And if you have more dimensions than 2, it's still Pythagorean theorem. It's still the same practice. That's all it is. Fred?
Just ask more like conceptually about this.
Yeah.
Even if it's weight as a factor, is the model automatically to reduce dimensionality and decides that there's a multiple that's reflecting itself? Is that a good way to think of it, or is that not?
Let me make sure I understand your question. You're talking about the weights here?
Yeah, if you put it like one higher or one lower, would that affect the model trying to reduce dimensionality? So that's like
No, but if you decrease the number of neighbors, you'll have less computation per data point. Yeah. It's not going to calculate the 10th neighbor if your n is 5 for each data point. But if your n is like 1,000 and you have 1,000 data points, you'll be making 1,000 calculations 1,000 times. That's that computational increase. Yeah. Cool. So out of sample accuracy, 97%. It's a tiny bit overfit, but that's great. That's great. And if you really want to have fun with K, you can loop through a range. I don't see a compelling reason to do much higher than 20, but we can say a range of 1 through 20 and say for K and K range, make a new model, set the neighbors to be equal to the K. So first time through the loop, your K is 1. You go with the 1 nearest neighbor. Second time through the loop, you go with the consensus of the 2 nearest neighbors for each data point. And so we see here for like why are some Ks lower accuracy, like 90% accuracy versus 93% accuracy? It's just because of the data itself. There's not some magic rule that 6 is a bad K. It's just on this one data set. It's not as great as 5 or 7. We get a little bit of a misclassification in that case. So there's not a magic number for K. Run through a couple. run through, yeah, 20 is fine. Depending on how many, how many columns you have, how many rows you have. Yeah. And if you wanted to see what this looked like on validate, I would be comfortable doing that as well. And then you could plot out the difference between validate and train, plot out the difference, et cetera, just like we did on the last exercise. Cool. So there's some other hyperparameters in here. I wouldn't worry so much about them, but definitely K is a big deal. And if you want to weight closer data points more strongly, then change your weights to the string distance. You can certainly play around with these other arguments, but the biggest ones are K and weights, in my opinion. And we'll get into some exercises. We don't have a huge amount of exercises. My recommendation is go through these on Titanic, then set aside some time to work through these on your telco. Right? So you can chip away at the project this week even further. Because we'll release the project tomorrow. The project presentations will be Tuesday. So really your project time is right now also. So we'll give you all time before lunch. Lunch is at 12. 12 to 12:30, pick up your lunch, heat up your lunch, whatever you got to do. And then at 12:30, Iris Gonzalez will be here. You're going to want to come to that one. It's a really good